My name is Chuck Knox. It is September the 7th, yes, Labor Day 2020. And I will be your Lidarian today, and we're going to talk about the use of LiDAR in the exploration of oil and natural gas. And this is a bit of a primer of what we're doing using LiDAR to track faults, fractures, and subsurface structures on the Earth's surface using light detection and ranging, and or known as LiDAR. What I want to talk about here is what LiDAR is and what LiDAR is not. And what LiDAR is an extremely accurate laser survey. And with the GPS, we know exactly where we're at, and we get perfect elevation surveys. Surveys can be very large, such as a statewide airborne survey, like we have here in Indiana, or it can be very small, such as a scan of a human tooth. The dental industry is even using LiDAR. It is a very powerful tool. It can strip away all vegetation and man-made structures to create a digital 3D image of the bare Earth surface. And that's what we're using is the bare Earth data to create these flow accumulation models, slope angle models, digital elevation models, aspect models. You can also measure tree canopy height. The forestry industry is using this, so many industries are using this, and it's a technology that is becoming increasingly important to many industries. But what LiDAR is not. In the oil and gas industry, it is not a standalone remote sensing tool that can, at this time, identify areas capable of producing oil or natural gas. What it is a good reconnaissance tool that allows us to identify areas that have potential, and then we can limit the area that we have to run 2D and then eventually 3D seismic. LiDAR works by measuring time when a pulse is sent from a emitter to when it is received by a camera, and you can send it from an airplane, from a drone, from a helicopter, from a car, from a backpack, from a handheld device. There's many ways to do it, and then what you do is you measure the time, angle, and intensity it comes back, the pulse comes back, and this translates into distance from a known sensor to object. GPS has been a big help in LiDAR. Just to be able to know exactly where you are on the face of the Earth has helped LiDAR. The laser scanning has been around a long time, but it's been the advent of GPS that has really made it quite usable. So you get an XYZ assigned to each pulse, and you get billions of these pulses on a big airborne survey. And the results are a cloud of points or a point cloud, and each point has its own coordinate and height. And then from that, we can learn things. Digital elevation models can be made, slope angle models, flow accumulation models, aspect models can be made. Many things can be done with a simple point cloud. There's some additional information if you would like to look up. There's some really quality work being done out there, and there's some past work that we use um, uh, to correlate the LiDAR to the surface. But the first thing I want to talk about is it's a National Geographic Channel show. It was the Lost Treasures of the Maya Snake King. And what they're doing is in Guatemala and in Mexico also they're going into the jungles and using LiDAR as a way to strip off virtually strip off the overgrowth so you can see what is underneath. Here's a 3D elevation model of a Mayan village in Guatemala. You can clearly see roads and buildings and temples and fields. And what LiDAR has been able to do for archaeology in these forested area has been astounding. They can now see areas that were totally covered in forest. The only way you would have found this before was to trudge through the jungle, which was impossible. The knowledge gained by these LiDAR surveys has expanded the scope of the Mayan civilization tremendously. This was much larger than we had thought before, and all due to these surface scans of the Earth by using LiDAR. One thing I want to do is go back and talk a bit about what the photogeologists of the post World War II area, what they were doing and how that relates to lidar. And one of the articles is a very informative article by P.H. Blanchette in 57, the development of fracture analysis as exploration method. And one thing Blanchette talks about is the method of why we see on the surface indications of subsurface faults and fractures. And he attributes this to the gravitational pull of the moon. And, this thing tugs twice a day on one side of the Earth and tugs twice a day on the other side of the Earth. And you get these flexings of subsurface faults and fractures. And this is the same as the tide influences the tide. It pulls on the water coming in and then lets it out. And so it's tugging on the earth at the same time. And he says on a daily basis, there's not you wouldn't think it'd have much influence, but you put it on geologic time and these fluctuations then they become compressed, and it's more like a tuning fork is what he talks about. So these faults and fractures underneath the earth's surface then have this energy that comes to the surface, and it had an influence on the glaciers, how the glaciers melted, and it also has an influence today as how stream flow is, the settling of sediments. This energy does have an influence on the surface. And I want to show you a bit of a analogy in Indiana, where I'm from, across the crest of the Cincinnati Arch. In the Precambrian is this ND pre-1600 eastern limit continental crust. This continental crust extends from Canada all the way to Mexico. Many of the major oil basins do hinge off of this. The Michigan Basin, the Illinois Basin, it goes through the mid-continent and all the way through into Texas then also. And in Indiana, it crosses right here. Take these out. And here's just a street map of Indiana, and it shows the ND pre-1600 eastern limit continental crust as it crosses from northeast Indiana into western Indiana. In northeast Indiana, this continental crust, this contact is manifested a great thrust fault from the east to the west. And what I want to do now is I want to put in the digital elevation model of Indiana. This is one of the larger surveys that is done out here. This is all, it took 3 years to do this. So here it is. This is the digital elevation model of Indiana, and you can see the moraines clearly. One of the important things you can see here is how the Wabash River system comes above this eastern limit 1600 line, and then follows this line as far as it can, and then it has to drop south. And then also the great Packerton Ridge up here, this great moraine that is up here. So as you can see how something that's 1.6 billion years old, as that eastern limit continental crust is, and how it influences sediments that are less than 14,000 years old. And so Blanchette then talks his theories on the tug of the moon, these tidal surges. It really has great relevance, and you can see it on a large scale across the Cincinnati Arch. Next is Lawrence Latman, and he has a article in 1959 which he talks about geomorphology applied to oil exploration. And what he has done is he has really documented the signatures on the surface that they were looking for back in the late 50s. And this is the basis of what I use today. I'm looking for these features on the surface with LIDAR. Next is an article by Frank Melton. It's aerial photographs and structural geomorphology. And Frank Melton was really goes way back. He was doing this surface work back in the mid 20s, even before the advent of aerial photography. So he was taking contour maps and then drawing in the stream flow and making analysis from that. And here is one of his flow accumulation models. As you can see, he would draw these in by hand, and then he was making calls on subsurface geology. And he was just a brilliant individual, and we can learn a lot from what he has to say. The next is an article I wrote for Lidar magazine back in 2017. It's using Lidar as an oil and natural gas exploration tool, and it has some good field models of what we're doing with Lidar, and is how they relate to oil and gas in Indiana, in Illinois Basin, and Michigan Basin. Here is the face of the Matanuska Glacier, which is outside of Palmer, Alaska. This is a good example of a small retreating alpine glacier, and fractures in the glacier allow meltwater to carry rock and sediment to the glacier base. Um, the faults and fractures of the Earth's surface do have an influence on glaciation and how they melt. It's not that every fracture in a glacier is going to be aligned with a subsurface fracture, but the glaciers did melt in a manner that was controlled by faults and fractures underneath. So the great continental glaciers we were dealing with out here in Indiana and Ohio and Michigan, the faults and fractures subsurface did have an influence in how they melted, and the signatures that were left behind by the melted glacier can be detected by LiDAR surveys. Next, I'm going to go into some field studies of what were the surface indications we're finding as how they relate to oil fields and different areas of the country. So first, I want to go up in the Michigan Basin. We're looking at Muskegon County right here. As you can see, what I like about this is up in here, you see all of these oil fields, these traverse oil fields. They follow this Muskegon, ancestral Muskegon River channel quite nicely. But what I want to go down is go down and then see these at Ravenna right here. And these are some very typical signatures that we see. Um, I like to put the imagery on so you can look at from the surface and how cluttered the surface is. You have trees and buildings and grass, and there's a lot to occlude your eyesight. So what I want to do is I want to put in the Ravenna fields. Then what I want to do is take away the imagery and then put in our digital elevation model. As you can see, without the culture, without the vegetation, the drainage patterns are quite clear. And one of the things we see a lot of is where these oil and gas fields are tucked away in these little three-sided baskets. So we'll see fault or fracture running this way, and then another one terminates into it here, and then a lot of times we're seeing another one right in the middle coming right out of it too. So this is a very common occurrence, and we see this in Michigan Basin, Illinois Basin, Cincinnati Arch, out in the mid-continent, out in Kansas, we're seeing it all. So you look over here, still a nice basket with an oil and gas field nestled right in the middle of it. Here is the what I want to focus on is the Geneva oil field, and this is in Van Buren County, Michigan, and it is a Travers age or Travers Devonian aged carbonate. Here's the imagery over the Geneva field, and you can see a bit of the flow, the stream flow in the area, but it's nothing like what you see when you go to the digital elevation model. Here's the Geneva field, and here's the Geneva area with the digital elevation model. And what I want to show you is the large basket area with smaller baskets. In the area, we have stream flow that crosses differing watersheds, parallel stream flow, this lattice work. Everything's quite textbook on this. Let's put in Geneva, right in this area right here. Now I want to go to Allegan County and look at this Overisel field up in the northern part, up in this one right up here. Again, plenty of culture, trees, grasses, not a lot of clarity to the imagery. Let's go to the DEM with the Overisel oil field. Now the DEM. And what we're seeing in Michigan, Indiana, and Illinois is where a moraine has a breach in it. A lot of times you'll get a fault and a fracture in that area, and Overisel really really follows this breach in this moraine right here. Now I want to go to the crest of the Cincinnati Arch in central Indiana. We have Blackford, Jay, Delaware, and Randolph counties of Indiana, and we're working on a Knox erosional remnant play there, and we're modeling these remnants, these subsurface remnants on the surface using flow accumulation models. And this is very similar to the Morrow County play in Ohio from the mid 60s. We're going to be looking at this area right here. Here is our imagery of the area. Again, there's quite a few trees. We do see some stream flow in this, so you can make some determinations just from stream flow on the surface with the imagery. But let me put in the DEM, and then you can really see the difference that the LiDAR makes. So we strip away all culture, all trees, and this is what we come up with. And it's still not very clear as to what's going on. But one of the things we can do with LiDAR is we can create flow accumulation models. So what I can do is I can digitally mimic where stream flow is and place this in. And so here's the flow accumulation model for this area of Jay County. Looks a lot like the Melton drawing, doesn't it? So with this, what we can do then is we can follow Blanchette and Latman's work as to draw in where these structural highs should be. And let's go ahead. Here we are. Let's put in the flow or the lidar derived highs using the flow accumulation models. And then we have been running 2D over these models with good success. Another area that we've been doing some work is out in the mid-continent in Rawlins County, Kansas. And this is a little bit more aged surface. It's had a lot of stream flow, time to create the stream flow on it. And we wanted to see what we were going to find using our LiDAR technology out in the mid-continent, out in Kansas and Nebraska. We're looking up in this area right at the northern part, right on the Nebraska-Kansas line. Here's the Rowan County, Kansas, the northern part of the county up into Nebraska. And one of the things we look at the digital elevation model here is we've got really good stream flow, and this gives us some good indicators of where subsurface faults and fractures may lie. I look at some of the things I look for is I look for this stream flow on one side of the watershed. I'm also looking for parallel stream flow, which we have abundant of this. It hits these at 90 degrees, and that's usually an indication of faults and fractures. And then we're seeing these stream flow lineaments or lineations across multiple watersheds, and that's where I then draw my lineaments. And well, let's go ahead and put the lineaments in. And so you can see there's quite a few lineaments in this area. So this leads me to an area that would have potential for running 2D. Another tool we have with LiDAR is slope angle. So I can measure the slope of the surface. And as you can see, the channels are yellow and red, and they have a higher slope angle on that. And then the green is flatter areas where the slope angle is less. And we can use this to track some things that might be imperceptible on the digital elevation model. We can actually track them on with the slope accumulation models. Let's put in the oil wells of the Kansas area in there, Kansas, Nebraska. And as you can see, they've had quite a bit of oil development in this area. So if we were to pick areas to run 2D, we have quite a bit to look at up in this area. Then here's the DEM with the oil wells in it. So, in conclusion, I want to stress that the geomorphic or the geologic principles developed by the photogeologists post-World War II, they can be applied to the results of the accurate laser scans of the surface that LiDAR provides. You know, where there is available LiDAR data, vast expanses of acreage can be examined quickly and economically. LiDAR data can be converted into a digital format that may be used in queries as scalable, and it can be displayed as both as raster and vector images. And most important is what we're using this for is the LiDAR data sets can be used to locate prospective areas to employ 2D seismic reconnaissance programs. And we've been having very good success using this, especially in the Cincinnati Arch of central Indiana. So again, I thank you for listening to this. And if you have any questions on LiDAR and how to use it in the exploration of oil and natural gas, feel free to call or send an email, and we'll go from there. Thank you.